What's up, AP Precalculus students? Let's get into Unit 3, Rational Functions. Polynomials divided by polynomials, essentially. And what happens when you're dividing polynomials is we get these interesting characteristics where we're going to focus on the lesson one. You can have a zero of a polynomial. You could have a vertical asymptote, with a rational, or you could have a whole. Key thing we learned throughout this first lesson is that zeros occur with fractions. If you take a number divided into zero, you get zero. So zero divided by anything is zero. One way I remember this is this number times zero is zero. Versus a vertical asymptote, if we end up with a number divided by zero, this is undefined. We're not allowed to divide by zero. Zero times nothing gives you a number. Just a way for you to remember that. We will investigate vertical asymptotes more next class. For right now, you're just going to kind of take it and run with it, that if you get a number divided by zero, you have a vertical asymptote. And then we have wholes, and wholes occur whenever your rational function ends up with 0 over 0. We investigated that in class, and how as we get close to the certain number and we get close to having 0 over 0, if you could cancel the zeros, you end up with like a location of the whole. So 0 over 0 could be really anything. We'll be able to find the location of the whole, either like the point location, or we'll use limit notation to find the location of the whole. But first things first, you're not going to have points whenever you have a denominator equal to 0. So our first question starts with find the domain. The domain is like, what are the x's that I could plug into this function g over f? So if I have g over f, what could I plug in to this? Well, we're not allowed to have a 0 in the denominator. So I'm going to just take the denominator and set it equal to 0 to find the x's we're not allowed to plug in. So I'm really just going to focus on the denominator here. Equal to 0. I'm going to factor positive 7 and negative 5. Multiply to get 35, add to get 2. And x cannot be 0 or negative 7 or 5. Negative 7, 0, 5. These are the values that we are not allowed to plug into our function, because we'd get a 0 in the denominator. And when we get a 0 in the denominator, we get undefines. Wholes have locations, but it's still a whole on our graph where we don't have a point. So we're not allowed to plug in that value because we're going to get a 0 in the denominator. Okay, and when we start looking at numerators and denominators, we realize, if you have everything factored and you have a 0, you're going to see that factor like x minus 1b in the numerator. You'll get 0 in the numerator when you plug in 1, and you'll get a number, hopefully, if you plug in 1. Whole being at 2 means you're going to have that factor in the numerator, x minus 2, and the denominator. Because if I plug in 2, I'm going to get 0 over 0. Boom, I have a whole. And then we have a vertical asymptote at x equals 3. That means the factor x minus 3 will occur once and just in the denominator. Now, here is my rational function. Just letting you know, like, if you plugged in 3, you'd get a number over 0 that confirms a vertical asymptote. If you plug in 2, you'd get 0 over 0. Now, let's talk about finding the location of the whole. Think about plugging in 2. Really, you're thinking about plugging in values close to 2. You're plugging in 2 into x minus 1, you get 1. You're plugging in 2 into x minus 2, you get something close to 0. You're plugging in 2 into x minus 3, you get negative 1. Plugging in 2 into x minus 2, you get 0, or really something close to 0. Now, if these numbers were close to 0, you could cancel those numbers, like divide the top and bottom by that small number, and you get this location. It's not that f of 2 equals -1, but rather the limit as x approaches 2 of this rational function is -1, or your hole's location is at 2, -1. Now, they didn't ask you to do that for this problem, but I'm just like setting up for the future. This is what we're doing when you're finding the location of a hole. Okay. It's like a bunch of true false questions, or cannot be determined based on this information. So we have a 0 at x equals 2. So I'm going to have x minus 2 as a factor in the numerator. Does not have a 0 at x equals 1. The denominator has zeros at x equals 2 and x equals 1. We don't have a 0 in the numerator at x equals 1. Okay. The multiplicities of the 0 at x equals 2 in the numerator and the denominator are equal. Okay. All right, so this is our rational function. Maybe there's some other stuff going on with numbers, but we're getting all of our zeros. They're telling us all of our zeros. So what do I notice? If I plugged in 2, I'd get 0 over 0. I have a hole. If I plugged in 1, I'd get a number over 0. I have a vertical asymptote. The hole at x equals 1 is false, as long as they're telling me all of the zeros of the numerator. And we're telling me we don't have a 0 at x equals 1, so that's definitely false. The vertical asymptote at x equals 2, that's false. As the multiplicities being the same, we won't have a number over 0. Even if the multiplicities were different, we'd still have a hole because of the 0 over 0. Cool. Okay. If a is 3 and b is 3, you'd have a cubed times x minus 2 over b cubed, or x cubed, over x minus 3. If I plugged in 0, I'd get this small number close to 0. Or if I plugged in something close to 0, I'd get this small number close to 0. You could think of it cubed times -2. I'd get this number close to 0 divided by -3. I'm plugging in 0. If you get these small numbers and they're close to 0, well, you could cancel them. All of them, the exact number. So this would be gone and this would be gone, which gives you this thing that like equals -2/3. Now, it doesn't equal -2/3. We're talking about like approaching 0. We're getting like a very, very small decimal that you can divide and cancel. So this is why we break out this limit notation that as x approaches 0, my function y is going to approach 2/3. And this is the idea that we talked about in the previous thing. This is like the location of the hole. It is good to see this so that you can kind of check to make sure everything's going well. I am going to break out Desmos for a couple of examples just to show you and to confirm myself that we're doing things correctly. So we have this x cubed x minus 2. We have x cubed x minus 3. And we're saying that at 0, you can notice that at 0, we have this undefined, we have this hole. So that's good. We are confirming that we have a hole. Now, as we get close to 0, if I plug in things close to 0, we can see my y values are very close to 0.66667. I can kind of show you, adding in a point, 0, 2/3, that our analysis was correct that this function has a hole at 0 2/3. Just to kind of show that, I'm going to just put it right there. Like that makes sense. 0 undefined, location is 0 2/3. Now, if A is 4 and B is 5, let's see how that changes things. Now, we still can't plug in 0 because we'd get a 0 in the denominator, but you would get something very close to 0 to the 4th over -2 and something close to 0 to the 5th over -3. Now, 4 of these very small numbers to the 4th will cancel with 4 of these very small numbers to the 5th. What happens is when I plug in 0, I'm ending up with like -2 over 0. I'm ending up with a number over 0. So what happens is we are talking about a situation where we have a vertical asymptote. So having like more zeros in the denominator than the numerator will develop us into getting a vertical asymptote. Confirming this, if I plugged in 4 and 5, we see now we have a vertical asymptote at 0. We don't have a hole at 0. Okay. But if we switch things and we got x to the 7th over x to the 6th, is it plus 3 or minus 3? It's minus 3. We'll talk about the notation for the vertical asymptote more. We'll use limit notation to describe the behavior on the vertical asymptote more next class. Here, if I plugged in 0, I'd have like numbers close to 0 to the 7th over this times this number close to -2. I'd have this number close to 0 to the 6th times this number -3. 6 of these very small numbers will cancel with 6 of these very small numbers. And I get 0 times -2 over -3. Now you're allowed to take a number and divide it into 0. You get 0. Now what we're saying is that we're not going to equal 0. Rather, for this situation, my function y has a hole at 0, 0. So we end up with 0 over 0 to start. We're not allowed to plug in 0, so that's bad. We still have a hole. I know you end up with 0 over a number. You might think that you have a 0, but at the beginning, if I plugged in 0, you get 0 over 0. Boom, that's your indication of the hole. Don't cancel anything. Okay, this is very important for rational functions. We don't like to cancel things until after we plug in stuff. When we cancel things, we can see what the dominating function is going to be. We can see that this function will end up looking like x minus 2 over x times x minus 3. But if you just looked at x minus 2 over x times x minus 3, x times x minus 2 over x times x minus 3, you might say, oh, we have a 0 at 0, not a hole. Here, if you looked at x minus 2 over x times x minus 3, you might say, oh, we have a vertical asymptote at x equals 0. You'd be correct with this one, but if you think we have a 0, a point at 0 because of your simplification, you'd be wrong. And I'll show you if I change this to x to the 7th, and this is x to the 6th, you might like, oh, I have a 0. Mr. Master, what are you talking about? But look at what I would get right here at 0, undefined. This is very important. Don't simplify first, because if you simplify, you might remove the fact that you do have a hole, and the hole has a location. So this is why we're going to say this guy still has a hole, even though you think like the x goes away and you don't have a 0 over 0 anymore. You do. This has 0 over 0. Same thing here. If you canceled out the x cubes and you're like, oh, the function's just x minus 2 over x minus 3. Like that's what the function will look like. However, you would remove the fact that this function has a hole at 0, 2/3. So like you can cancel after you really analyze your zeros. Don't cancel too early. because you can. The original function is the original function. What numbers can or you cannot plug in is very important. So don't simplify early. Okay. Now we're talking about multiple rationals that we are going to combine. And the question is, what input values, those are x values, are the output values, those are y values, equal to 0. So we're going to take this g function and we're going to set it equal to 0. Now, for rational functions to be able to manipulate them, we want just one rational to be able to analyze them. We just want one rational, like what is the top divided by the bottom. This is how we're going to do it. We're going to need a common denominator. Like if I told you, hey, what's 2/3 minus 3/4, you wouldn't just say it's like -1 or +1 or something like that. You know, you need a common denominator multiplying the fraction by the other's denominator to create a common denominator. Make sure you do a little bit of analysis in case you have like one of the factors there. So like you just get the simplest common denominator or the least common denominator. So that's what we're going to do here. We are going to get a common denominator. Now, when we do this, it's important to not do too much work. What do I mean by that? Like the denominator leave as x minus 5 times x minus 4. That's in a nice factored form. That is fine. We like factored forms. They are easy to work with. So leave both denominators as x minus 5, x minus 4. We'll be able to combine them in a second. Keep this minus or distribute this minus to that -3. Remember, like if you're subtracting a fraction, 1/3 minus 2/3, you're not going to say the top and the bottom are negative. You're going to say, oh, this is -2/3. And then you can combine them like this and be -1/3. This is one way to do it. I like to do it that way. I'll do it both ways. Or you keep the minus sign, and if you keep the minus sign, the 3 stays as a positive. You can either write out 3 times x minus 4 or go ahead and just like distribute. I get 3x minus 12. Go ahead and distribute here. I get 2x minus 10. Now, the reason why we distribute for the top and we don't on the bottom is because when you subtract or add fractions together, the denominators don't change, but the numerators do get combined. Okay, like 2/3 plus 1/3 are 3/3. Very important to understand that with fractions. Don't change the denominator, just add the numerators. Well, here I'm going to be subtracting 3x minus 12. If we wanted to write this all out as one fraction, the common denominator stays, the x minus 5, x minus 4. The numerator would be subtracting the 3x minus 12. All of it. I use a set of parentheses to know that I need to distribute this negative, so it's -3x plus 12, giving me 2x minus 10. I'll just go ahead and combine this stuff. -1x, -10 plus 12 is +2 over x minus 5, x minus 4. When will this equal 0? When the top equals 0, we get x equals 2. That is my answer. It's a lot of work to get that answer, but it's necessary. Let me just show you like what I'm going to do in the future because I like to do it. I think I make less mistakes. I will distribute this negative to the 3. I'll distribute the -3. I'll get 2x minus 10, and then I'll get -3x plus +12. I only deal with positives. I don't have to worry about a big set of parentheses because I'm distributing that negative into that 3 over the common denominator, x minus 5, x minus 4. When does this equal 0 is when the top equals 0. You can combine, boom, you get that -x plus 2. X is 2. Cool. So we'll see more of those later. All right. Utilizing your knowledge from last unit, combining it with your knowledge of this unit, we create these great questions where I'm going to give you a graph of f and g. And tell you and ask you like, hey, if it's f over g, what do we have? Holes. Like what's going on at 1? What's going on at 2? If I have g over f, what's going on? To be able to do this, it's going to help to have the equations, at least a form of the equation of f and a form of the equation of g. Now, they don't give us a y-axis. We don't want the exact equation, but there are some things that we do know. We know this is a negative x to the even. So like that negative leading coefficient, probably something I need to pay attention to. This is a positive x to the odd. That leading coefficient x, probably something I want to pay attention to. So what would be the equation for x? Well, we see a 0 at 1, so that means the factor x minus 0 has to be there. We see a 0 at 3. X minus 3 has to be in there. We see a 0 at 4 that bounces off and doesn't change signs. X minus 4 squared is going to be a factor of f. We can do the same thing for g. We'll have x minus 2, x minus 3, x minus 4. All right, now let's look at the equation A. Let's write it to the side. It's f over g. So here's the equation for A of x. It's f over g. Okay. If I plug in 1, I get 0 over a number. This is a 0 of the graph of A. Don't simplify anything or stuff is going to disappear on you. The function as it's written is what we are analyzing. If I plug in 2, I'd get a number over 0. A number over 0 indicates a vertical asymptote. If I plug in 3, I get 0 over 0. This is your indication of a hole. Let's find the location. If I plugged in 3, I'd get 2 times it's not plugging in 3 again, it's plugging in a number close to 3. I'd get 2 times 0 times negative 1 squared, which is positive 1, over 1 times 0 times negative 1. If these numbers were close to 0, we could cancel them. They'd go away. I end up with 2 over negative 1. I find that as x approaches 3, my function a of x approaches negative 2. This is my hole's location, 3 comma negative 2. And then let's talk about 4. If I plugged in 4, I get 0 over 0. That is another indication of a hole. Now, if you plugged in 4, you'd get 3 times 1 times something close to 0 squared. You'd get 2 times 1 times something close to 0 to the first. If you could cancel some things, you would cancel these factors, these zeros, these things close to 0. One of them would cancel. You would get 0, which is telling you that this function's hole has a location of 4, 0. Now, I probably made a big mistake here. What is the mistake that I made? Go back to what we talked about. Now, it might not be exactly what we're talking about, but that negative for f is important. I should have had a negative to start. I should have some negative here. What's that going to change? That's going to change the hole's location. Now, it might not be exactly at this location, but let's just assume. I think what the problem is asking you is just like, do we have a hole or a vertical asymptote or a 0? But let's say we knew the exact equation was this negative 1. That would change the location of your hole for this guy. It'd be a positive 2. Let's just see it. If you had negative x minus 1, x minus 3, x minus 4 squared. over x minus 2, x minus 3, x minus 4. We are saying that the function has a 0 at 1. Boom. A vertical asymptote at x equals 2. Boom. A hole at 0, comma 2. Well, that looks right. And a hole at 4, comma 0. That looks right as well. That's if I have that negative there. If it was a different number, it would change the locations of this hole. If this was like a -2, this whole location would change. All right, now let's look at B. B is the same thing as A, just flipped. So B of x is x minus 2, x minus 3, x minus 4. And then a negative x minus 1, x minus 3, x minus 4 squared. All right, if I plugged in 1, now I'll get a number divided by 0, indication of a vertical asymptote. If I plugged in 2, I'd get a 0 over a number, indication of a 0. If I plugged in 3, I get 0 over 0, indication of a hole. Let's pretend that we have the exact locations. Let's find the location of the hole. Plugging in 3, I'd get 1 times 0 times -1 over -2 times 0 times +1. If I could cancel the zeros because we're talking about getting close to it, I'd get +1/2, which is the flip of the location from A. So I would say the limit as x approaches 3 of this B function is +1/2. That's the location of the hole. As we get close to 3, my y values are getting close to 1/2. If I plugged in 4, I still get 0 over 0. Now this one's the tricky one, because we get 0 over 0. However, since the x minus 4 being squared in the denominator overwhelms the x minus 4 in the numerator, we would end up with a 0 in the denominator, which is telling me that we have a vertical asymptote here. So it's a weird one. If I have 0 squared over 0, the hole's location is 0. If I have 0 over 0 squared, oh, I actually don't have a hole. This is actually an indication of a vertical asymptote. So it's almost like I need to kind of pay attention to the amount of zeros and their location. Let me just kind of show you. If I got 2 times 3 times 0 over -3 times 1 times 0 squared, yeah, one of these zeros will cancel with one of those zeros, but I still have this 0 in the denominator. So I'm paying attention to the amounts of zeros. So up here, this I probably should say is 0 squared over 0. And that is confirming that I have a hole located at 0. Tricky stuff. Doesn't usually show up, but let's see what happens if I flip these. Okay, so x equals 1 is a vertical asymptote. X equals 1 is a vertical asymptote. That checks out. X equals 2 is a 0. X equals 2 is a 0. That checks out. I have a hole at 3. The location is 3/2. 3/2 checks out. I thought I had a location of a hole at first at 4, but turns out I have a vertical asymptote because the zeros in the bottom overwhelm the zeros in the top. So that's what we got. Cool. Okay. I'm giving you the graph. You have to get the information out of the graph to produce the equation to find what A and B is. What do we notice? We got a vertical asymptote at x equals 3 and x equals negative 3. Well, that means that B's got to be 3 because I'm going to have the factors x plus 3 and x minus 3 in the denominator. So boom. What else do I notice? I have a hole at x equals negative 2. Well, that means x plus 2 must be A. A has to be 2 so that I have x plus 2 over x plus 2, giving me a 0 over 0. And then I have in the denominator x plus 3, x minus 3, whatever order. Okay, so A is 2, B's got to be 3. What is the location of the hole? Now, if this is the equation, they're giving you the equation, let's find this. If I plugged in x equals negative 2, because that's the location of the hole, I would get a 0 over a 0 times 1 times negative 5. If those zeros could cancel, what happens when we cancel things? They don't go away. They turn into ones. This is a big mistake students make, is that they think that this is 0, but in terms of like when you cancel numbers, divide the top and bottom by the same number, you're left with ones. So I think that the limit as x approaches negative 2 of this function f of x is negative 1/5. If I look at the graph, it does make sense. Negative 2, it looks like it's a negative value. Again, I can graph it and find that that exact location is like negative 0.2. Okay. Same deal here. What's A and B? Well, we see x equals negative 2 is a vertical asymptote. So that means x plus 2 has got to be in the denominator. We can see x equals 6 is the location of a hole. So that means x minus 6 has to be in the numerator and the denominator. So in this case, A is negative 6 and B is positive 2. It's okay to have negative values if this is a plus. And the other one, I had to have the plus and the minus just so you knew which one's A and which one's B. All right, what is the location of the hole? Well, if you have 3 times x minus 6 over x minus 6 times x plus 2, if I plugged in 6, I'd get 3 times 0 over 0 times 8. If the zeros, these values close to 0, as we plug in values close to 6, we're not getting zeros, we're getting values close to 0 that can cancel. We'd get this 3/8. So I would say the limit as x approaches 6 of this function g of x equals 3/8. This is an easy enough one to graph and see. Three times x minus 6 over x minus 6 times x plus 2. Okay, vertical asymptote at x equals negative 2. That checks out. Hole's location is at 6 comma 3/8. 6 comma 3/8. Yep, that makes sense too. If I plugged in 3 or 6, again undefined, what is the location? Close to 3/8. Okay. Giving you a table of values, making sure you can interpret and understand what's going on. Giving you a function too, that helps you out. What do we notice? You can't plug in 4 or 6 because you'd get a 0 in the denominator. Where does your graph have a hole? Well, you know you can't plug in 4, but you can see that as we get close to 4, we're getting close to a half. As you get close to 6, your values are getting larger in the negative direction or the positive direction. What am I getting from this is like, I can't plug in 4 or 6, but through like looking at the table, I can kind of tell that x equals 4 is the location of a hole. And it has a y coordinate, it's approaching 0.5, whereas x equals 6 is going to be a location of a vertical asymptote where my values are getting larger and larger. So x equals 4 is the hole. The limit as x approaches 4 of this function is going to be 0.5 or a half. I can kind of tell my y values as my x values get closer to 4, getting closer to 0.5. Where does your graph have a vertical asymptote? It's x equals 6. Why? Because my function values are getting larger and smaller, or larger in both the negative and the positive direction. That means A's got to be 4 for my graph to have a hole at 4. Good question. If I look to the left and the right of 4, my values are both getting closer to this 1/2. To the left of 4, I'm close to, oh, geez. We made a mistake here. Heads up on the homework. That should be a negative value. I got to tell everybody. I'm going to tell everybody. Negative 1/2. Now, to the left of 6, 5.99 is to the left of 6. My values are getting close to, or not getting close to, they're getting larger in the negative direction. But to the right of 6, my values are getting more and more positive. We're going to talk about this more next class, this vertical asymptote behavior. This is just like a challenge for you to kind of understand. Like, to the right of 6, my y values are getting larger. To the left of 6, my y values are getting larger, but in the negative direction. Mistake on our table. Okay. To understand rational functions, it's going to be helpful to have things factored. The bottom is easily factorable. The top, we might have to do some thinking / figure it out. Excuse me. I know it's got to be 2x and x. I know I have to have 15 and 1 or 5 and 3. 5 and 3 works if this is negative 5 and this is positive 3. I'll get negative 10x and positive 3x to give me negative 7x. Use whatever technique you would like to have that numerator factored. You can do a times c, rewrite the middle using a box, or just figure it out. Vertical asymptote, got to be at x equals 1. You're going to get a number over 0. Hole at 5. I can tell it's at 5. If I plugged in 5, I'd get 10 plus 3, which is 13, times 0 over 0 times 4. So 5, 13 fourths is the location of the hole. My 4s are just really looking bad these days. Where are my zeros? When the top equals 0 and there's not a 0 on the bottom, 2x plus 3 would be the only factor. Negative 3/2 would be my 0. And that's it. I think this unit will be more challenging than the last unit. You really have to kind of understand what's going on. We're going to give it to you in different ways. Giving you the equation, giving you a graph, giving you a table. You got to be able to handle things. We're going to give you graphs of polynomials that you had to know how to write the equations for from last unit. Boom, that's going to show up. So like, it's going to be a little bit harder than last unit. So let's do our work and we'll be all right. Cool. I am out.